First question, if the mass of a radioactive sample is doubled, the activity of the sample and the disintegration constant of a sample are respectively. So first of all, we know that activity depends upon mass, but a disintegration constant, that is lambda, doesn't change. So correct answer for this question is option A, that is increases, the activity of the sample will increase if the mass of the sample is doubled, but the disintegration constant will remain the same. So correct answer for this question is option A. Moving towards the next question. When a sample of solid lithium is placed in a flask of hydrogen gas, then following reaction happened. Hydrogen plus lithium will going to give you 2 molecules of helium. This statement is, so first of all, the given reaction is a nuclear reaction, which can take place only if a proton, that is a hydrogen nucleus, comes in contact with a lithium nucleus. If the hydrogen is in the atomic form, the interaction between its electron cloud and the electron cloud of lithium atom keeps the two nuclei from getting close to each other. Even if isolated protons are used, they must be fired at the lithium atom with enough kinetic energy to overcome the electric repulsion between the proton and the lithium atom. So this statement is false. Correct answer is option B. Looking towards the next question. Consider an initially pure m-gram sample of an X element, an isotope that has the half-life of T hours. What is its initial decay rate? Okay, so we know that N is equals to N naught e raised to minus lambda T, or I can write as dN upon dt is equals to N naught lambda e raised to minus lambda T. Okay, so at T is equals to 0, so this will be at 0, so dN upon dt at T is equals to 0, therefore N naught will be equals to N naught lambda. Okay, now where N is the initial number of undecayed atoms, and that undecayed atoms can be written as mass of the sample upon mass of single atom of an element, that is the atomic weight upon Avogadro's number. This is nothing but equals to M into Na, the whole upon A. Okay, so therefore dN upon dt at T is equals to 0 is equals to M Na lambda, the whole upon this N naught ki jagah I have placed this, the whole upon A. M given is 0.693, M Na the whole upon lambda given over here, that is this upon A T. This is half-life formula. Lambda can be written as 0.693 upon T. So if we look over to the options, we have this in option C, 0.693 mNa upon AT. So correct answer for this question is option C. Moving towards the next question. Which sample contains greater number of nuclei? First example is 5 micro Ci, that is Curie, sample of plutonium-240 with half-life 6560 years, or a 4.45 micro Curie sample of americium-243 with half-life 7370 years. Okay, so first of all, we know that the activity minus dN upon dt is equals to lambda n, and therefore n is equals to minus dN upon dt into T half, that is the half-life, the whole upon log to the base e of 2. Okay, now taking the ratio of this expressions for plutonium-240 to the same expressions for plutonium-243. We have N of plutonium upon N of americium, which is equals to minus dN of plutonium upon dt into T half of plutonium, the whole upon minus dN of americium, the whole upon dt into T half of americium. When we substitute the values over here, it gives you 5 microcurie into 6560 years, the whole upon 4.45 microcurie into 7370 years. And when you solve it out, it gives you ratio 1. That is, the two samples contain equal number of nuclei. So correct answer for this question is option C, that is equal in both. Moving towards the last question, the fusion of uranium-235 can be triggered by the absorption of a slow neutron by a nucleus. Similarly, a slow proton can also be used. This statement is correct, wrong, information is insufficient, or none of this. So because the neutron has no electric charge, it experiences no electric repulsion from uranium-235 nucleus. Hence, a slow-moving neutron can approach and enter a uranium-235 nucleus, thereby providing the excitation needed to trigger fission. By contrast, a slow-moving proton feels a strong repulsion from a uranium-235 nucleus. It never gets close to the nucleus, so it cannot trigger fission. So correct answer is option B, that is wrong. Option B.